Okay. Well, why don't we go ahead and get started? I'm really happy to introduce David Alvarez-Melis. David received his bachelor's degree at ITAM and then a master's at the Courant Institute in math. And then he went on to Boston. So he did his PhD at MIT, working with the machine learning group there, including Tommi Jaakkola. And then more recently, he's been a postdoctoral research at Microsoft Research in New England. And he's worked on a lot of kind of interesting issues that come up as we start thinking about machine learning deploying in the real world. In particular, he'll tell us today about some things that arise with limited data and interpretability needs. So David, please go ahead.
Great. Thanks a lot for the introduction, Eric. I'm very happy to be here in the seminar. Thanks for the invitation. And yeah, so today I prepared a talk that is a two-part story about the difference between the idealized and the real-life machine learning settings and what to do about it. And I was told that there would be a mixture of different audiences and fields, so I prepared a talk that is sort of mostly at a high level, but then I'm going to take some deep dive into some of the details, and I'm happy to stop for questions throughout the talk. So if there's any kind of urgent questions, just shoot them. And if not, I'm going to make a pause in the middle. I can take questions there and then towards the end. So yeah, so to set the context for the motivation of this talk and my work in general, I usually start with a mandatory machine learning is amazing slide. So we're all familiar with these success stories and some very highly visible domains and tasks. Some of them showing superhuman performance. But for every success, there is a failure. And some of them might seem funny, like the ones I'm showing here in this slide, but some of them are deadly serious, and they can have a profound impact on the lives of people affected by them. So there's clearly a discrepancy here between the successes and the failures of machine learning that we see in the news. And a natural question is, what explains this difference? So what's going on here? So I claim that if we look at the success stories that I showed in the previous slide, and in general, other success stories, we'll see that they concentrate in a few set of domains that have they enjoy some very specific conditions, let's say the idealized conditions, in which most of machine learning in practice does not. So how are these two paradigms different, the idealized and the real-life machine learning paradigms? So to begin with, in the idealized setting, it is usually assumed that we have abundant data. But in practice, most applications don't have too much data. So we have scarcity, especially for labeled clean data. Likewise, computational resources tend to be limited in applications. We have evaluation metrics that are not always clear from the outset, and we face several constraints in terms of deployment. So there's several constraints that limit the way we can deploy and apply these models in the real world. And as you see from this very simple diagram, I see most of the discrepancy between these two paradigms concentrating towards the first and last steps of this very simplified machine learning pipeline. So on the data and society sides. So a natural question is, what are we doing as a community about this? And I think this is where the problem comes in. So I think that our approach to dealing with these discrepancies, and to be honest, to most of the problems in machine learning, looks a little bit like this. In terms of percentage of effort, thinking, and papers devoted to each of these three steps of the pipeline. So this is probably the most, if not the only important thing I'll say today. And it's the fact that I think that today, some of the most pressing problems in machine learning are rooted in the data and society parts of the machine learning pipeline, and therefore cannot be solved by thinking about models alone. We need to think about data and society too, sort of at an equal level as models. So going forward, this is where I would like to see the field of machine learning going, with sort of equal amounts of thought going into data and society, and bringing these two often forgotten parts of the pipeline back into the spotlight. In particular, there's two aspects of these first and third chunks that I'm very excited about and I've been working on for the past few years. So the first one is a data-centric view of machine learning that puts data as a focus and not just as an afterthought of the learning process. And one that goes beyond accuracy and consider things like robustness and trustworthiness of the methods as a kind of principal component of our pipeline. And what I really like about these two areas of research is that they intersect many different disciplines and fields, ranging from differential equations to philosophy and cognitive side on the other side. And as a heads up, all of these fields will make an appearance in the talk today. So my goal for the talk today is to convince you, those of you who are not convinced, I know that many in this department are already convinced and I'm preaching to the choir, but those of you who are not, to convince you that these two areas of research, so the data and the society parts of machine learning, have many exciting areas of research for all tastes, ranging from theoretical to very applied. So I think there's something for everyone here. Okay, so for today, I'll sort of split the talk into two parts. The first one will deal with data, and in particular, we'll look at different methods to amplify data sets to deal with the data scarcity problem that I talked about before. And our main workhorse here will be optimal transport, which if you haven't heard of it, you're not familiar with it, I'm gonna introduce it in a couple of slides. And then the second part of the talk will focus on my work on interpretability, in particular, making interpretability methods robust and more human-centered. Okay, so for this first part of the talk, I want to kind of remind you of this discrepancy that I talked about before between the idealized and real-life machine learning scenarios in terms of data. So in real life, we usually deal with limited or messy data. And it could be, so here I'm using limited or quote-unquote scarcity in a very broad way. It could refer to settings where we have data only from a similar domain, not exactly the domain that we care about. It could be that we only have unlabeled data and we're trying to solve, let's say, a classification task. Or it could be that the data we have is restricted in some way. For example, it has some privacy constraints imposed upon it. And I want to hone in on a few settings where these discrepancies sort of become fundamental. So for example, in the setting of transfer learning, we usually assume that we have a small target data set with limited data, and then we have access to additional data sets where we can pre-train and initialize our models. And then the question is, how do we choose which one to use for pre-training our models? In the distribution-driven scenario, we assume that the distribution that generates our data sets is changing through time, and we need to account for that. And then in the distributed learning scenario, we assume that we have a collection of multiple small data sets. Here you can think of user individual kind of language models on their smartphones. And then we want to learn on an aggregated version of these. So roughly here, we're talking about different types of operations on data sets that range from comparing them, interpolating between them, and aggregating them. And despite their differences between these three verbs, I claim that there's three fundamental mathematical concepts hiding behind all these operations on data sets. And I'm talking about the notions of correspondence, distance, and transformation. So these are kind of building blocks of operations between data sets, if you will. And what if I told you that there's a framework that sort of unifies these three notions of these three mathematical notions under the same umbrella? And it's a field that has very rich theory spanning 2 centuries worth of theory, and it has also fast algorithms. So it might sound too good to be true. I thought it was at first, but luckily for us, it's not. And of course, I'm talking about optimal transport, which is a sort of fundamental theoretical framework at the intersection of applied math, statistics, and optimization that has been used in various subfields in computer science. And of course, I'm going to provide an introduction in the next slide. But before doing that, I want to emphasize why I think optimal transport is such a cool framework to tackle these problems. So as I said before, it has very mature theory, which we can rely on for results and to provide a theoretical backing to our results. In the past 5 years, there's been a lot of work on scaling up these algorithms and making them much more applicable to the big data sets that we have in machine learning, especially on solving approximate versions of the optimal transport problem. And last but not least, it's a very flexible framework. So the way that the problem is built up, it allows for a lot of geometry and a lot of domain knowledge to be specified and injected into the problem. So it makes it really applicable across domains and problems. Okay, so for the first part of the talk, I'm going to show you how to use optimal transport to align data sets, to compare them, and to transform them. Okay, so a quick recap in a nutshell of optimal transport. So the best way that I found to describe optimal transport is the same one that Gaspard Monge, one of the forefathers of optimal transport, was thinking about when he proposed it almost 3 centuries ago in France. So living in 18th century France, Monge was very interested in optimal ways to transport coal from mines to factories. So here I want you to think of mines and factories associated with a location, let's say in 2D space, X and Y. And since we have these coordinates, we can compute pairwise distances between each pair of points. And we'll have some supply and demand constraints on the amount of coal that is produced and can be received in each of the factories. So this is the general setup. And what we're trying to find is an assignment of mines to factories that minimizes the total transportation cost. That is the total distance traveled by the coal from mines to factories. So this is the original formulation of the problem that Monge came up with. But soon after some time, it was clear that this formulation was too strict and didn't always have a solution. So along came Kantorovich almost 2 centuries later, and he proposed to relax this problem. And the relaxation he proposed consists of what we call mass splitting, which basically means what it sounds like. So we allow the coal, the mass from each of the mines to be split and sent to multiple factories. So now we can have pairwise movements across each of these source and target points. And we'll quantify how much mass is being moved between each pair of points to these variables gamma ij. And the cost associated with each of these movements is, of course, the amount of mass that we move, gamma ij, multiplied by the distance that we move it. So the distance from xi to yj. As before, we're trying to minimize the total transportation cost, so the sum of all these individual costs. And in order to make sure that we're not creating or destroying any coal in the process, we need to impose some linear supply and demand constraints. So this is it. This is the classic discrete optimal transport problem, also known as the earth mover distance in the computer vision community. And of course, here I used mines and factories, but you can readily see how this generalizes to more kind of general settings. So first, we can think about general discrete distributions. So we can think of distributions consisting of empirical sums over samples. The problem in this case is a finite linear programming problem where we're trying to find a matrix that collects all these gamma j's, all these movements of mass. And this matrix, we call it the coupling. And a nice thing about this is that it can be interpreted as a soft correspondence between the two datasets. So the two distributions. Once I find this matrix, I can look at the entries and look at how much mass is in each of those entries. And I can interpret that as a notion of matching, of soft matching or correspondence between source and target points. And for the purposes of this talk, we'll stay on the discrete world, but I just want to quickly mention that this easily generalizes to continuous distributions. And most of the theory is phrased in terms of more general distributions that might be continuous or discrete. So of course, for continuous distributions, the problem now becomes infinite dimensional, and we have essentially a joint distribution, gamma, instead of a matrix, capital gamma. So these are the kind of two general settings of the problem. But as I said before, we'll stay on the discrete setting for the purposes of this talk. And as many of you know or are already kind of anticipating, when the choice of cost is taken to be the distance in the space, the optimal value of this problem is called the Wasserstein distance, which is, I guess, the name by which most people know optimal transport. So the p-Wasserstein distances are optimal transport problems where the cost is distance to the power of p. So that's the p-Wasserstein distance. Okay, so we don't care about mines and factory. Well, we might, but in general, we care about datasets in this talk. So we will have two datasets like these two, and then to compare them to use optimal transport, we'll basically do what we did with the mines and factories. So we'll start by computing pairwise distances between each data point in the two datasets. And then implicitly, when solving this problem, we're trying to find an optimal correspondence, an optimal matching matrix gamma that minimizes the total distance between these two datasets. So the number that we get out of this can be interpreted as a notion of distance or dissimilarity between the two datasets. And that's how we will use it here. Okay, so the first couple of papers that I want to highlight use this notion of distance and correspondence for its kind of most fundamental aspect, finding correspondences across datasets and aligning them. And this is based on joint work with my PhD advisor, Tommi Jaakkola, Stefan Jegelka from MIT, and Yusuf Mehryar from IBM. So the motivation here will be the problem of machine translation. which, as I'm sure you're aware, requires tons and tons of data. And in particular, it requires tons of parallel data. So what this means is that we have collections of documents, let's say in English and Spanish, and then we have correspondences, let's say at the sentence level between each sentence in the two data sets. And with this, we train a machine translation system. But what happens if we don't have any parallel data? So this could be the case, for example, when we're dealing with two languages that just don't co-occur too much in practice, like Telugu and Spanish in this case. So we might have monolingual collections of documents in the two languages, but we just don't have any prior translations between them, so no way to initialize these machine translation systems, so no supervision to begin with. So the idea that we had, and that many other people have had, is to use word co-occurrence statistics to find correspondences between the two languages. And for now, we'll do it at the level of words, which is the simplest building block for machine translation. So when I talk about co-occurrences, what I mean is the following. In linguistics, there's this phenomenon that the meaning of a word can be characterized by the words that it co-occurs with. So if we look, for example, here at the words house and casa, its translation in Spanish, we expect them to show up in similar contexts, surrounded by similar words, because they have similar meaning across the two languages, right? So one is the translation of the other. So if we compute the counts of all these co-occurrences and we put them in a huge matrix of size vocabulary times vocabulary, we hope that there's enough signal in those matrices to allow us to find correspondences between the two sets of words. Of course, if we deal with these matrices directly, we have huge matrices in the two languages, and that might be too expensive to compute or to even store. So instead, we'll find a compact representation of this, the word co-occurrence information. So QN word embeddings, which, as I'm sure many of you know, are essentially just that. They're a compact representation of co-occurrence information derived, let's say, with a neural language model or something else like Word2Vec. So now we can take these word embeddings, assuming that they have this co-occurrence information implicit, latent, hiding inside them. And then we've turned our problem into a simpler one. So we take our collections of documents, we use our favorite word embedding algorithm to get a point cloud for each of the two languages. And now the problem boils down to a point-wise correspondence. So we have two point clouds, and we're trying to find a correspondence between them in a fully unsupervised way. So without knowing any of the point-to-point correspondences a priori. And looking at these two point clouds, we put our optimal transport hats on, and we can recognize two empirical distributions. So we can treat these two point clouds, these two collections of words, as support points of a discrete distribution with uniform weights for now, let's say. And then we can treat this as an optimal transport problem, where we're trying to find we're trying to compute pairwise distances between the two sets of words to find a correspondence between them using optimal transport. So we would start by computing these pairwise vector-to-vector distances. And this is basically what the first OT approaches in NLP did. But for the case of translation, there's a fundamental flaw in this approach. And the problem is that we're sort of implicitly assuming that the two spaces are globally registered. And what I mean by this is that roughly, for example, if you look at the cluster of colors, pink and red in English, I'm assuming that the cluster of colors in Spanish is sort of pointing in the same direction in the space. But this is really, there's no reason why this should be the case, especially because word embedding algorithms tend to be rotationally invariant. So just as well, we could have gotten a different random seed, and then let's say the Spanish dictionary, the Spanish word embeddings would be completely rotated. And without knowing prior correspondences, then we're backing this problem. We don't have a notion of distance that we can use for optimal transport because we just try to compute naively distances across the two spaces. This is going to be meaningless. There's a rotational invariance that this distance is unaware of. So this is a problem that we're dealing with. Of course, this is an instance of a much more general class of problems where we had two embedded data sets. And we assume that A, we don't have any prior correspondences, so no prior translations between them. But furthermore, the spaces themselves are not in correspondence, so they're unregistered. And the ultimate goal is to learn correspondences between the two collections of points, the two data sets. So I'm going to quickly talk about mainly one approach that we propose to tackle this problem. And then in passing, I'll mention another approach, both of which are based on optimal transport. So the first approach relies on choosing an invariance class of transformations, let's say rotations in this case. And then just augmenting the optimization problem with a minimization over these kinds of transformations too. So in contrast to the classic optimal transfer problem, where we're just trying to find this matrix of correspondences, now we're also trying to find, let's say, the best orthogonal matrix, the best rotation between these two spaces simultaneously. And by doing this, we're sort of making the optimal transfer problem invariant to the classes of transformations that live in the family F. And of course, this is not new. Variations of this objective have been proposed in many contexts, for example, the iterative closest points algorithm. But many of these have appeared in the computer vision community, and owing to this fact, they tend to be tailored to 2D or 3D shapes, and they don't have great scalability beyond that. And just to give you an idea, for raw embeddings, we're talking about embeddings of size, let's say 200, 500, 1000. So we really need something that scales up well with dimensionality. So the formulation we propose is sufficiently general that we can capture many settings where this problem arises, yet it's efficiently optimizable. So it provides a good trade-off between those two. So what is the approach we propose? So in a nutshell, what we do is characterizing the invariances that I talked about as sets of matrices with bounded Schatten norm. So as a reminder, Schatten norms are matrix norms. They're spectral matrix norms that englobe many popular matrix norms, like Frobenius norms or the nuclear norm. So because of this, they have a lot of modeling flexibility. We can model everything from rigid transformations to projections. And the nice thing about using this class of transformations is that we show that the inner problem, this minimization, has a closed form solution under some very simple assumptions. So this is, of course, nice. And then the other problem is still a classic optimal transfer problem on gamma. So once we fix P, this is just a classic OT problem that we can solve with one of these very fast recent algorithms for optimal transfer. So naturally, this suggests an alternating minimization approach, where for a fixed gamma, we obtain P through this closed form solution that relies on a single value composition. And for a fixed P, we obtain gamma epsilon approximately using the synchronal algorithm, which is kind of the main linchpin of computational optimal transfer. And then we repeat. So this is the algorithm we propose. So what can we use it for? So first, just kind of to demonstrate it on simple data sets, I'm going to take a point cloud, and then I'm going to apply a random orthogonal transformation. And this is what I'm showing here. And then I'm going to run classic optimal transport, and I'm plotting the matrix gamma. So the correspondences colored by whether they're correct in the sense that they're matching corresponding points. If they're incorrect, it's going to be red. And when they're correct, it's going to be green. So for this particular data set, you can see that using classic optimal transport fails miserably. And there's no expectation why it shouldn't, because it doesn't know anything about this rotation. It's just trying to greedily minimize closest points. And therefore, it fails in finding these correspondences. In contrast, when we inject these invariants or orthogonal transformations in the optimal transfer problem, we're able to recover the correct correspondences. And this, of course, occurs across many simple data sets. But I motivated this from the point of view of machine translation. So that's where we're heading now. So as a reminder, we left off this problem at the point where we had embedded the two collections of documents into a vector space. And we were trying to find correspondences between these point clouds. So I talked about this approach on using orthogonally invariant optimal transport. And I'll quickly mention this other approach that we proposed that relies on another generalization of optimal transport, pre-existing generalization of optimal transport, called the Gromov-Wasserstein distance. And the gist of the Gromov-Wasserstein distance is that instead of comparing points directly across the two data sets, it compares distances or relations across them. So the good thing about this is that it's agnostic to these transformations. We're just going to look at, let's say, the pairwise distances in one domain and in the other domain, and then we're going to try to align the similarity or distance matrices. So this sort of lifts the problem away from the ground spaces where they're defined, and then it boils down to a correspondence problem between similarity matrices. So again, we find a coupling, which we can interpret as a correspondence and use that to find translations. So these are the two approaches that we'll compare. And we'll compare them against, first, a very strong supervised baseline. So this relies on using an initial seed of translation, so a seed dictionary, and then the classic Procrustes alignment method. So this is a strong baseline in the sense that it uses labels, it uses supervision. But despite this fact, this breakthrough paper by Kono and colleagues in 2018 showed that by using an adversarial neural network approach, they were able to surpass, with this fully unsupervised method, to surpass the very strong supervised baseline provided by Procrustes alignment. So this was very shocking to the NLP community at the time. And then a few months later, we proposed our approach that actually matches and outperforms the adversarial neural network approach. So for a time, achieving state-of-the-art in this task. But more importantly, the beauty of this approach, I think, is when we look at the runtime and we compare it against the adversarial neural network approach, both of these are orders of magnitude faster. So we get comparable or even better performance at really orders of magnitude speedups. And before kind of closing this chapter, I just want to mention that in follow-up work, we show how we can extend this framework now to compare hierarchical data sets. So here you can think of ontologies or phylogenetic trees. And basically everything is the same, but with a twist that instead of operating on Euclidean space, we operate on hyperbolic space for various geometric reasons. And then we define hyperbolic analogs of everything I described so far. So the alignment is now given by a hyperbolic neural network. And the matching is now done through an optimal transport that uses the hyperbolic run metric. And we show that this works. And in fact, we are able to propose the first principled and fully unsupervised approach to ontology matching. So to the best of our knowledge, this is the first approach that doesn't use any, let's say, lexical surface level information of the ontologies and only uses the geometry to align them. So this is sort of a cool extension of the invariant OT approach. Okay, so now I'm gonna switch gears and talk about computing distances between labeled datasets. So the key here is, so far we've been talking about just feature datasets, unlabeled datasets, but now we'll talk about labeled datasets. And the motivation here is what I talked about before in terms of transfer learning. So one of these kind of classic settings where we're trying to leverage additional data. So as I mentioned before, we might have a target data set of interest and then multiple possible pre-training data sets, huge labeled pre-training data sets that we might find online. And then the question is, for our task of interest, which of these should we choose? So which one is the best pre-training data set? And of course, intuitively, we would say, well, we should pick the one that is closest or most similar to our target data set of interest. But similar in what way? So this is the key question that we're trying to answer here. Given two labeled datasets, let's say MNIST and Fashion MNIST, which are two classic benchmark datasets in machine learning, how do we define a notion of distance between them that is able to sort of deal with many challenges that arise in this setting? So first, we might have datasets that have different number of samples. They might have different label sets. So in this case, MNIST, for example, is a dataset of digits labeled 0 through 9, and Fashion MNIST is a dataset of clothing items like shirt and pants. So even though we're dealing with completely different labels, is there something about the geometry of the two datasets that we can use to define a notion of distance between them? And finally, as always, we want something that is ideally efficient and model agnostic. So the approach we propose can be conceptually broken into two steps. The first step is to define a notion of distance between the labels, the discrete categorical labels. And to do this, we characterize the labels as discrete distributions of the samples that have that label. So for example, for MNIST, the label 2 would be described as a collection, a distribution over the images that are labeled 2. And we would do the same for the bags on the other side. And with this, we now have two discrete distributions in our hands, and we can use optimal transport, for example, to define a distance between them. So here we'll use the Wasserstein distance. And with this, now we have, for each pair of labels, we can define a distance between them. So we sort of lifted the problem of comparing discrete labels, and we pushed it back to the feature domain and define a distributional distance there. So with this, in turn, now we can define a notion of distance between each data point in the two datasets. Here, data point consists of a feature, an image, and its label. So we can simply combine the feature distance, let's say pixel to pixel distance, or something fancier in terms of filters or something else that operates on the features. And then for the hard part, which is comparing the discrete labels, we use what I just described, this Wasserstein distance between their associated distributions. So this is going to be the ground metric that we use for the optimal transfer problem. And we'll compute it for every pair of data points in the two data sets. And then, as we did before, we'll lift this pairwise notion of distance into now a distance between the entire collections of points. That is the datasets. So we end up with this optimal transport dataset distance. That is just apart from the ad hoc ground metric that we use. Otherwise, it's a typical classic optimal transport distance. So we're minimizing this total matching cost. And again, the matching, the optimal coupling can be interpreted as a soft correspondence. And being an optimal transport distance, it has some nice properties. For example, it is a true metric in the mathematical sense. And we show that it can be computed even for very large data sets by using a Gaussian approximation on these per label distributions. So with this, we can compute it in very large data sets to the scale of ImageNet or other equally large data sets. Okay, so what can we do with this notion of distance? So as I motivated this from the point of view of transferability and transfer learning, let's see what we can do in that case. So I'm taking 5 data sets that, as you can see, have different kinds of labels, so digits, clothes, letters, etc. And then the first thing I'm going to do is I'm going to compute pairwise OTDD distances between these two, and this is the heat map that I'm showing here. And then independently on the side, I'm going to run a transfer learning pipeline, a simple transfer learning pipeline that consists of pre-training a large neural network on the full data of one of the domains, and then fine-tuning with a small amount of data of the target domain. And I'm going to repeat this for every pair of data sets. And this is what I'm plotting here. So just as a heads up, I'm using the initials of the data sets just to keep the plot clean. So in the y-axis is this notion of transferability. So higher is better. It means that we were able to transfer more successfully the model across these two data sets. And on the x-axis is our notion of distance, which, as any distance, lower numbers correspond to more similar data sets. So the key takeaway here is that there's a strong and significant negative correlation between these two quantities. And what this means in practice is that we can use this notion of distance to predict or anticipate which data sets are likely to result in good transfer. And we can use it, for example, to narrow down the list of potential data sets that we want to train our models on. So this saves us a lot of compute in terms of refitting models and trying different data sets. So the key takeaways here is that this notion of distance can compare any two classification data sets, regardless of their labels. And it's, to our knowledge, the first notion of distance that can do this. And it's principal, scalable, and as I show in this plot and many other experiments in the paper, it's highly predictive of model transferability across tasks. Okay, so the last thing I want to talk about in this first part is transformation. So now we'll move from what we've been doing so far, which is static comparison of data sets, and we'll move into a realm of modification. And for this last part, this is more recent work, so I'll just give kind of the highlights. So the motivation here will be what I call dataset shaping. And what I mean by this is we start by an initial dataset, and we have some objective that we want to impose on this dataset. For example, we might want to obfuscate some sensitive attributes. Maybe we want to increase class separation so that any model that we train on this data set is likely to perform better. Or maybe we already have a model in mind, it's been pre-trained and frozen, and we want to maximize its accuracy when applied to this data set. So despite their dissimilarity, we show in this paper that all these problems can be cast under the same framework, in the same language of dataset optimization. So here the optimization and everything will be phrased in terms of distributions. So we're trying to minimize an objective given by a functional in the space of probability measures. And the dataset that we're trying to find will be the distribution that minimizes this objective, perhaps subject to some constraints. So I'm talking about distributions, which, as you know, in general, are live in infinite dimensional space, non-Euclidean space. So this is a very challenging problem. And just to kind of be specific about the kind of optimization problem we have, you can think of this space as a space of distributions or data sets where each point corresponds to a data set. We have an objective defined on that space, and we're trying to find the minimizer of some objective function. There's many ways to approach this. And the way we chose to do it is through the formalism of gradient flows, which is a linchpin of applied mathematics. The beautiful thing about gradient flows is that they've been studied in very general spaces, including a probability space. So there's a very rich literature on theoretical aspects of these flows, which when talking about probability space, they're characterized by partial differential equations of this form. But of course, this gives us a theoretical backing to formulate the method, but we need to solve it computationally somehow. So we need to discretize it in two ways. We need to discretize in space and in time. And after doing this, we end up with a particle approach, which basically looks like a collection of gradient step updates on each of the particles. Here, a particle is one data point, one image, and then they're coupled by this functional objective F. So in a nutshell, this is the approach that we propose, and then I'm going to show you what we can use it for. So first, in a very simple setting, toy 3D dataset, imagine we have this initial dataset, and we want to transform it to replicate the reference dataset rho star with a caveat. We want whatever distribution that we get to be linearly separable. And I'm going to show you the resulting datasets after flowing them with this method using different objectives. So first, using just an objective based on the distance between datasets, as a sanity check, we see that we can recover the reference dataset. So this is expected, but good to see. If we only use the linear separability constraint, well, we get a linearly separable dataset as expected. But of course, the interesting case is when we combine these two and we run the flow, and you'll see that we can recover a dataset that geometrically is similar to the reference dataset, but indeed is linearly separable. So we're able to capture this constraint and shape our dataset accordingly. Moving on into more interesting and realistic applications, I want to kind of highlight this possible application consisting of model repurposing. So here, I want you to think of a model that has been trained on a large pre-training dataset like CIFAR10. So we train a model, it has high accuracy, and now it's frozen, and we can't touch it. And then there's a new dataset that arrives, let's say this histopathology dataset, that we're interested in classifying, but we don't have too many samples. So we can either train a model on whatever samples we have from that domain, or we can try to leverage the inductive biases that were learned by this network on this much larger but unrelated dataset. And since we cannot modify the model, the only thing we can modify is the data, and that's what we're going to do. So by using a functional flow, using the distance between these two datasets, I'm going to transform the target dataset, the histopathology dataset, towards CIFAR10. And I'm going to show you what the accuracy of this pre-trained and frozen model looks like as we flow the data. So there's two relevant baselines here. One is what happens if we don't do any adaptation and we just take this frozen model and throw it into the histopathology dataset. This is binary classification, so we'll roughly get 50% random chance. And the green line is what we get if we train a simple but good model just on the data from this target domain that we have, which is not much, so we get around 80%. And now for a sample of points that I'm showing here, we'll see how they evolve as we run the flow between these two domains. And you'll see, I don't know if you can see it here with the resolution of my computer, but you should see some artifacts appearing in the images, very subtle. But yet, if you look at the accuracy of the network, you can see that it's going up to the point that it surpasses what we would have gotten if we just trained on the samples from the target domain. So basically what's happening here is we're repurposing this network, this model, to apply it on a data set with samples that it has never seen. So it has never seen imaging data, let alone from this specific task. So we are able to repurpose it for that. So this gives us sort of a new framework to formalize and solve data transformation problems. Okay, so I think this is a good point to make a pause. The second part is much shorter, so I think I'm doing good in time, but I'm happy to pause here and take any questions on the first part, or I can continue. And yeah, so if there's any questions, I'll wait now for a couple of seconds. Okay, yeah, so feel free to save those questions for the end. I'll continue for now. So for this shorter second part, I just want to give you a glimpse of the work that I've been doing on the interpretability space. And what I want to kind of motivate this from is the exact paper and example that got me interested in this problem, in this field to begin with. And it's a paper by Ribeiro and colleagues where they run a very interesting experiment. So they train a very good network to distinguish between huskies, images of huskies and wolves. So they get near perfect accuracy, everything looks good, but there's a problem in this model, and it's fundamentally flawed in one important way. And I'm sure you'll be able to figure out what the problem is once I show you an input image and an explanation that their method, so they propose an interpretability method, provides. So this is an example that is misclassified as a wolf, even though it's a husky, and the explanation that the framework shows, so basically you can interpret this as the important pixels for the model, they're all focused on the snow. So by looking at this, you can see sort of what's going on here. The model is overfitting to the snow, so it's picking up this spurious bias that in fact was on purpose injected into the data. So the authors made sure that all the images of huskies are in non-snow backgrounds and all the images of wolves have snow in the background. So basically they train a snow detector. But the really interesting thing here is what happens when you let humans interact with this model. So first, before showing the explanation, most users look at the accuracy and they trust the model because it seems very good, and very few pick up on this artifact. Whereas after they show the users the explanation, the trust in the model completely plummets, and most users are able to identify the spurious bias, even those who are non-experts in the task. So this is a kind of very crisp example of, I think, the power of interpretability for debugging in this case, but of course this goes beyond debugging. It can have implications and ramifications into fairness, causality, and many other aspects of machine learning. So to kind of set this in context, I'll just want to draw a distinction between the two main paradigms of interpretability. So one is the classic statistics type model-based interpretability, where we expect the whole model to be interpretable and understand each component of the model. And as many of you are aware, machine learning has gravitated towards a more point-wise notion of interpretability in recent times, which basically focuses around prediction, providing explanations for specific predictions. So for example, in image classification, after predicting a cat here, a possible explanation would be, let's say, a heat map that points to the pixels that led to this prediction. And this is quote unquote the explanation. There's two main types of prediction-based methods for producing explanations. There's gradient-based methods, which I'm sure you can imagine what kind of things they do. And then there's perturbation-based methods, which in a nutshell, they take the point that we're trying to explain, they generate perturbations around it, they fit a simple model around it, and then they use this local surrogate model as the explanation. So if you're familiar with LIME, which I'm sure many people here are familiar with, that's an instance of this. So, okay. Now that we sort of set the context for this post-hoc prediction-based interpretability, let's talk about the robustness. So once I started working on this topic, I had this intuition going in that similar inputs should yield similar explanations in order for the explanations to be meaningful. So we set out to test this on many popular interpretability methods. And we came back with a resounding no as an answer. So we found that most of these methods are actually very sensitive to small changes in the input. So to give you an example of the kind of experiments we did, we would take an image in a classifier, train on it, and produce an explanation with one of these popular interpretability methods, which could look something like this. And we add a tiny amount of noise, tiny enough that it's imperceptible to the human eye, but yet it leads to a very dramatic change in the explanation. So this is just based on eyeballing, but we can formalize this through a notion of robustness, like Lipschitz robustness. So we formalize it by looking at maximal deviations of the explanation in a small neighborhood. And this notion we can compute across samples, across data sets, aggregate it, and then compare these interpretability methods according to this Lipschitz continuity metric. So this is what I'm showing here. Higher numbers correspond to less robust models. So you can see that in general, these methods are not very robust, but especially perturbation-based methods like LIME are especially sensitive, so not very robust. So the key takeaway here is that these local explanation methods are not very robust. And a natural question is, can we robustify them? So in follow-up work, we propose one possible way to robustify these methods. And the intuition behind this work is that one of the main sources of instability of these perturbation-based methods is the post-hoc estimation step, so the sampling and estimation step. So instead of doing that, in order to avoid that, what we can and we try to do is to have a model that predicts and explains simultaneously. And this is sort of the holy grail of interpretability, to have a model that immediately and in conjunction with the predictions, it produces an explanation justifying it. And the way we propose to operationalize this is through a parameterization of a model that sort of looks like a linear model with two big caveats. One is that the coefficients are not constant. They're input dependent and they can vary through space. And the model operates not necessarily on raw inputs, but maybe on higher level representations of the input. For example, patterns or textures in an image. And in order to keep this interpretable, we regularize it in a way that the coefficients do behave like coefficients of a linear model locally by reducing its Lipschitz constant. So we're making it locally robust. And one way to achieve this is by essentially adding a gradient penalty that smooths out the changes in these theta coefficients locally. So with this, we come up with a neural network architecture that uses this optimization as part of the end-to-end training, and then we train it. And I'm going to show some results on what we get with these networks. So first, I would be remiss not to show that it actually leads to more robust explanations. So this is what these two plots are showing. So again, using the Lipschitz metric, we show that the explanations produced by this method are much more robust. But of course, robustness and interpretability without performance is futile. So we also show that we get very decent performance with these regularized networks. And in fact, in some cases, the regularization imposed by this local Lipschitz constraint actually gives us better generalization, which could be explained by the model being smoothed out implicitly as the explanations are regularized. So as a key takeaway, regularizing for explanation robustness doesn't degrade and sometimes even improves the performance of these models. Okay, so the very last thing I want to talk about is this very recent work on a different view of interpretability, which now is centered around the human aspect of interpretability. So the motivation for this work was the observation that the ultimate goal of machine learning interpretability is, of course, to explain to humans. But this might be lost or might not be obvious if you look at some of the papers in this community where humans often appear as an afterthought of the process. So instead, we set out to put humans at the front and center of the interpretability pipeline. And our starting point was the question of what it means for a human to explain. And luckily for us, we can stand on the shoulders of giants here because the nature of human explanation has long been studied in the social sciences, in philosophy, and in cognitive science. So there's a very, very rich literature on human explanation out there. So we surveyed this literature and we found some universal principles of human explanation emerging, which we think are not captured by current methods. So to give you an example of the kinds of principles that we found, I'm going to contrast what these disciplines observe versus what machine learning interpretability does right now, at least most methods do. So according to these disciplines, we humans tend to explain in contrastive terms. So we might say something like fever is more consistent with pneumonia than with something else. We also often use counterfactual statements. For example, had the patient had something else, then the diagnosis would be something. And importantly, when we're trying to explain complex phenomena, we tend to break up the explanations into a sequence of simple premises, each one easily digestible by the other person that we're trying to explain to. And all these three are in contrast with what current interpretability methods do, at least most of them, which tend to be absolute, only produce factual explanations, and tend to explain in one shot. So for example, all the pixels in an image in one shot. So after proposing these postulates, these observations, these principles, we distill them into a set of postulates that we claim are important for human-centered machine learning interpretability. And these are contrastiveness, modularity, exhaustiveness, parsimony, and intelligibility. And I'm happy to go into details of these in the Q&A session. But for now, I'll say that in order to formalize this, we need a framework that is consistent with these principles. And we found it in the notion of weight of evidence from information theory. So this notion has been around for a while, so it's well understood. It it's consistent with these principles, and it's sort of very intuitive because it's phrased in terms of things like evidence and weight, which are intuitive to most people. So it satisfies our design principles. And the only kind of downside, it's that it's been mostly used in simple settings. So in order to apply to general machine learning settings, we had to extend it in multiple ways. But we do that in this paper, and then we build an interpretability tool around it. To evaluate, as I promised before, we also we come full circle and we come back to humans after being inspired by them. And we run a user study with machine learning practitioners to evaluate the use of our tool. So this consists of two parts. There's a tutorial where we explain all the background concepts needed to understand the weight of evidence, and then a study where we ask the participants to answer some questions about the predictions of a model using this tool. So the main findings are that the modularity, so the ability to break up explanations into simple premises, was very appreciated by the users. We had some level of interactivity, but users requested even more interactivity, and that just goes to show that interactivity is a fundamental aspect of interpretability that we cannot forget, and this links to HCI, and there's, of course, a lot of work coming from the HCI community on this. And finally, the tutorial was fundamental. It was really appreciated by users, and we observed a clear correlation in the time spent and the quality of the answers of the study with how much time was spent in the tutorial. So we end this paper with sort of an open call for interpretability researchers to provide hands-on tutorials with their tools. Okay, so with that, and in the last minute or so, I'm going to close with a recap of what I talked about today and some ideas for next steps. So I started with this kind of call for a balanced machine learning research agenda that puts data and society back in the spotlight, back at the forefront along with models. And then in the first part, I talked about various approaches for what I call dataset amplification that rely on the theory of optimal transport. So we talked about correspondence between word embeddings, distances between labeled datasets, and then transformation of labeled datasets. In the second part, I talked about the societal implication of machine learning, in particular in terms of interpretability. We talked about the robustness of popular interpretability methods, and then I closed just now with this recent work on a human-centered view of interpretability. Okay, so in terms of kind of next steps that I think are interesting in these two directions, the first one in terms of interpretability starts from the takeaway, the observation that this interpretability performance trade-off that people talk about in machine learning can perhaps be mitigated. But what if this is the answer to the wrong question? What if we're not even measuring the right notion of performance? So what I mean by this is, in machine learning, we typically measure accuracy of a model. And even for transparent, explainable, interpretable machine learning, we still look at the same notion of accuracy. So we look at the predictions of a model sort of in a vacuum. But in real application, especially in high-stakes applications, there's typically a human who's taking these predictions and then having the ultimate, the last word on the prediction. So I claim, and many other people claim, that what we really care about is a notion of performance that really takes this end-to-end view of the problem, and we look at the final prediction, the final decision made by the human. And of course, this is not radical, this is not new. There's many people in the machine learning and HCI communities working on this. And I think that this kind of poses an interesting question of whether there's still a trade-off in terms of performance and interpretability, even in this case, once we take this broader view of evaluation. For the data-centric work that I presented, I see all these parts of the puzzle as fitting within a unified framework of data-centric machine learning, which is sort of orthogonal to the current prevailing machine learning model-centric ML type setting, which, as you know, is sort of fundamentally centered around parameters. So optimization is in parameter space, regularization is in parameter space, data is assumed to be fixed, and adaptation, when it happens, it's a model that adapts to the data. In this new paradigm, the optimization problem is in dataset space. Regularization also operates on data. And of course, as a consequence of this, the data is dynamic and modifiable. And when we need to adapt, it's the data that adapts to the model. So these are sort of complementary but orthogonal views of the problem. And there's plenty of open problems, both practical and theoretical here. And with that, I'm going to close with some acknowledgements to my collaborators in these papers, some pointers to resources. So most of the code that I presented here is in these two repos. And there's a cool visualization of the OTDD in this blog post, in the MSR blog post, that I encourage you to check out. And with that, I'm happy to take questions in the couple of minutes that we have left. Sorry for running so long in the talk, but hopefully, yeah, we can get a couple of questions in.
Okay, thank you. I'm sure we're all virtually thanking David for a great talk. We do have time for a question or two. You can put it in the chat window, or just go ahead and unmute and ask if you have one. So I had a question about actually more on the first part. So when you were doing the transfer learning and computing distances between data sets, right? So you emphasized that you had a metric, which of course is symmetric. But I noticed in one of your performance plots that there were some cases where there was a big discrepancy between the sort of two distances of transfer. So one data set helped the other much more than vice versa. So that's a sort of fundamentally non-symmetric notion.
Yeah.
But I'm wondering if you have any insights for why that happens and how there might be hope to kind of like identify that asymmetry when you're talking about this sort of like data alignment and comparison.
Yeah, no, that's a great question. So by choosing a notion of distance that is an actual distance, then this is sort of unavoidable. We have asymmetric notion. And indeed, as you point out, typically in transfer learning, there's an easy direction and there's a hard direction. And that's sort of what you see in that plot, that one of the two directions tends to be easier. And the way to understand what we're doing is basically sort of averaging those two distances. So if you notice in the plot, we sort of have a line of best fit that goes in between those two. But of course, that's not the last word. That's not very desirable in applications. We might want to have something that captures that intrinsic asymmetry between the two tasks. And there's different ways to go about this. I think many of them will imply a different type of representation, or at least a tighter integration with a model. So you can sort of build in the, let's say, training error of your model into your notion of distance and enhance it with that so that you get something about the complexity of the data set there. I think there's also notions of work from the dynamic view of optimal transfer that we might be able to apply. So understanding transfer as total work done in a physical way might give us an insight in how to model asymmetry of model performance across domains. But yeah, what you're saying is a fundamental downside of this approach, that it's symmetric, and ultimately we probably want something more specific, more granular, that is asymmetric.
Okay, thank you. Any other questions?
I might have missed it, but what's the time complexity to calculate the optimal transport metric that you had earlier? Yeah,
so that's a great question. I didn't mention it, but so if you solve it exactly, it's a linear programming problem. So you have the typical LP complexity, so it's cubic. Recently, there's been a lot of work on, as I mentioned before, on fast versions of solvers for the OT problem, which solve it only epsilon approximately. And for those, you basically get near linear complexity. So near linear in the number of variables, with, of course, some dependence on the epsilon of the approximation. So there's a very interesting line of work there. So if you're interested in algorithmic aspects of that, I would point you to the monograph by Marco Couturi and Gabriel Peyre, Computational Optimal Transport. Or there's also, many recent NeurIPS and ICML papers that focus on the complexity side. But yeah, so roughly nearly linear.
Thanks.
Yep.
And I guess with approximations, when you do the alignment of data sets, you can avoid the explicitly computing distances between all pairs of data points, because of course that would get out of hand quickly.
Yeah, so there's several types of approximations possible. One is subsampling. So you can subsample points from your two data sets and then use that. And that's typically what we do for very large data sets, like image net. This Other approximations, they basically, what they do is they add an entropic regularization term on the optimal transport problem that makes it strongly convex. And thanks to that, you have better complexity. But the effect of that is roughly smoothing out the coupling. So instead of getting a dense, a sparse matching matrix between the data sets, the more you regularize, the denser this mapping becomes, which sounds undesirable, but it turns out that in practice, this regularization often helps, especially in misspecified problems where the matching is not perfect. Smoothing out over these matchings sometimes improves performance. So it's actually, yeah, it has a kind of win-win flavor to it.
Good. Okay, so we are after 2, so we should probably wrap up. But let's thank David again for a great talk.
Yeah, thanks a lot for the invitation. It was a pleasure.